this up so you can see my screen, right? All right. So we'll be giving you a link to access this workbench, and that will be mmm.tools.msquare.club. So it will lead you to this login page. It might change, the looks might change later on, but yeah, basically you'll be given a username and password to access this workbench. So you just use that, get log into it, and you are greeted with multiple options here. So there are four main options. You launch a machine, you delete that machine, which is like killing it completely, or you stop a machine where you're just like shutting it down and keeping it for later, or you restart a machine, like you run into some issue or you stopped it and you want to restart the stopped machine, you have that option. So to get started, to get access to this Robin, you click on launch a machine. You come to this page on the left side, you would see build with parameters, which is basically just an option to select like what kind of a machine do you want. Like there are small machines which have less compute power, and you have super large ones which have more compute power. So you can just select one of them. I'll just go with the default, it's large, and you click on build, and you see this processing, and you can click on this in progress button and go to the console output on the left side. So you see what is happening in the background. You don't need to worry about anything that happens here. Like at the end, you would be shown a URL and a username and password that you can use to access that workbench instance that you spin up. So we'll just give it a few seconds. Yeah, let's spin it up. Yeah. So here you would see this information. This is all that actually matters for you. So you can take a copy of this, save it somewhere else, and because like once you close this page, you might not have access to it again. So just remember to copy paste your username and password. And this is different from the username and password that you entered earlier. This is going to be a new one every time you spin up a new instance. So what you would do is you would click on this link to create, open it in a new tab. You can just do that, and you would be greeted with a separate username and password prompt. And there you can use the parameters shown here. Don't need to save it anywhere, and it'll take a minute, and it'll give you the RStudio environment for you to run it, run the Robin model. So since it might take a few minutes, I already have one up and running. I can show you that one. So when that opens up, you get into this UI. This is RStudio UI. And what you would have is a terminal console and few files in the right-hand side. You would have all of these except for the last one. So what you can do is click on this base mmm script.r file, which would open up this file here. Maybe I'll just check if the other one's open. Okay, never mind. So it'll take some time to open up. And in the meantime, I'll just start explaining what is happening here. So this is a basic set of code that you can use to run a model using the Facebook's demo data. We added some extra bits at the end so that you can combine the results from this model run into one Excel sheet, which you can later use to understand. Like because Robin, when it usually runs, it computes up to 10,000 models, and you don't want to go through each of them manually and look through it. So initially we have some steps here that is the setting up the environment, and you have a in this case you have a simulated data that we are loading, and we are just setting that as the model input data, the data which we are going to model with. And how that looks like is shown here. Like when you run head model input data, you would see this format. So this is the format that Robin expects you to give the data in. You have the date and the dependent variable revenue here, and few other media variables or non-media variables. So you usually like the naming convention would be underscore S for spend and like underscore I or clicks for anything else. So this is the format Robin expects you to give the data in. And there's also a separate thing called Profit, which is also a library developed by Meta uh, to process time series data. And in Robin, it is used to model holiday, seasonality, trend, and weekdays, those kind of parameters. So you have access to that. And how that looks like is simply like this. Like you have a date, you have a name of the holiday, you have which country that holiday is for, and the year. Like it has a lot of data in there. So that's the default data that they provide you. You have the option to use your own data if you want to. And we just set up a directory where all the results and all the input data is going to be presented. You don't need to change that. Like you can just, this is the directory we are referring to. And the first step for setting up the Robin model is telling it like, what are the inputs for Robin? Okay, so first thing we set up is the model input data that we saw earlier. And the second one is the holiday data that comes from the profit holidays that we see here. And we also mentioned which is the column name in the model input data that contains the date parameter. So that is date, as you saw earlier. And we tell like, what are we trying to model? We are trying to model for revenue or like conversion. Like, what is the type of the dependent variable? So the revenue or conversions, you can mention that. And depending on that, you would see like the Robin model would try to give you an ROAS or a CPA. So that is that. And you can tell like what all profit was you want to use. So if you want to use trend, seasonality, and holiday, you can mention all of them. There's also weekday option for businesses like that have specific behavior in weekdays and weekends. So you can add that too. One thing you need to remember is that actually two things. So the profit variables, when you mention them, they're modeled for the whole data that you give. So if you're giving a 4-year data in your model input data, these variables would be modeled for that whole data. You can't specify window for them. So they're going to be modeled for the whole of that. But anything else, like the media variables and non-media variables, they would be modeled only for the modeling window period that we mentioned. And the other thing is all the holiday variables are combined into one single variable, and only one coefficient is applied for that. Like it's modeled as a single variable. So if you want a behavior, or if you want to understand, for example, how the Christmas holiday affected your sales, you wouldn't be able to do that if you do it like this. So you would want to give that as a separate variable. So how you would do that is using context wars. So these are variables like competitor sales or other events and even extra holidays you can give here. You can add that as a separate variable, and then that will be modeled separately. Just one thing to remember is that if you're going to do that, just remember to remove it from the original profit holidays table, so that you don't have run into a multi-collinearity issue because there's data in both the tables. It would be better if you can remove it. And yeah, the one parameter I missed is the profit country, because there is data for multiple countries here, the holiday data for multiple countries. So if you're modeling for a US client, you can mention like, the US region, the holidays only referring to the US holiday. And the next one is paid media spends. The paid media spend is basically all the media marketing spends that your marketing spend data that you have. And then you have paid media wars, which is the model, the variable that you want to model. Usually, in the case of Robin, this is going to be spend itself. Like we would advise you to use spend whenever possible because when you're using exposure, like impression or clicks, like it's there's some amount of uncertainty. Even Robin has agreed to it, like the developers of Robin. So they usually rely on spend. So only one thing that you want to remember is whatever you're giving in paid media was and spends, they need to be in the same order. So if you're starting with TV here, it should start with TV here. You can mention the same name if you want to use the spend itself, or you can, for example, in this case, you see Facebook spend is given here, and what you want to model is for the impressions. So that is also an option. But we would advise, yeah, using spend would be a better option. And there's also an option to add organic variables. Those are variables which you don't spend money on, for example, newsletters or emails. So they can be added here, and you have a modeling window that you can set and an add stock function. So you can mention three kinds of add stock functions here. So geometric is the easiest one and the most simplest one. I'll come into the details of it. And there's also variable CDF and variable PDF. So you can choose which one you want to use. And yeah, so the next part of it is you can plot an add stock and saturation graph. This also I can show you how it looks like once I cover this topic. So once you set up the inputs, you want to set up some hyperparameters based on the inputs. So since you chose geometric, since we chose geometric above, and the parameters we would set for that is theta. So how geometric works is that like you have a fixed decay function. So if you say theta is 0.5, and it's 50%, if the media effect is 100% in the first week, in the second week, it would decay down to 50%. And the third week, it would decay down to 25% of that. So every week you lose half of the effect. So that's what geometric does. Consistently cut it down by half. And for Webull and Webull CDF, you have an option to allow for a variable decay rate. So as the weeks progress, you can change the decay rate so it decays faster. That is what Webull offers, and those are better for digital channels. And if you have channels which have a late conversion, or like the peak of the media's effect comes much later, then you can choose Webull PDF, which is more compute intensive, but it allows you to have a delayed effect, which the other two options does not allow. And so the parameters that you see here, the third one, theta, is for the add stock function, and you have separate theta for each of the variables. We mention it in the form of a range. You can even give a fixed value. When you see here C0 and 0.3, that means the theta of Facebook should be somewhere between this range. Robin will try to handle like what should be the ideal value when it runs all this modeling. It will try to find what is the ideal value for Facebook's theta here. And you would see two other parameters, which is Facebook alpha and gamma. This is for modeling the response curves. So how that looks like is, I'll just give an example. Okay, so you see Robin uses the hill function to model the response curves. And it has two parameters, alpha and gamma, as you've seen. Alpha is controlling the shape of the curve. So you get more S-shaped curves as you increase the value. And gamma will control the inflection point, like how fast it, like what is the highest point it gets to, or when does it saturate? Like that is what the gamma defines here. And these are how the values will look like. for each of how the curves look like for each of the values. And yeah, and let's come back here. We like the values set here are like the recommended values that we give for the digital channels and the non-digital channels, like TV, search. You can, of course, change them, and you can even give a fixed value to know for sure how those response curves should look like. And the last parameter here is the training size. So here again, we are given a range of values. So the training size should be 0.5 to 0.8, meaning use 50 to 80% of the data for training and use the rest for validation and test. So that's the idea here. And Robin will try to use more data and less data as it goes by each iteration. So once you have set that up, you can, the pre-processing, all the setup is complete. Once you do that, and you can go directly into Robin to run.
Hold on, Suji, hang tight. Kadisha has a question. What's your take?
Yes, well, my brain is lagging behind, so I want to make sure I'm understanding what you were saying about the parameters. Can you move up to where you were showing those? So essentially, I'm assuming the numbers in blue each represent one of the variables from the previous model. So it could be the actual, or are you saying that each of those numbers is like the actual channel, and this is saying how that parameter is going to impact the channel? Is that what that's representing?
Right. For example, when we say the Facebook spend theta should be from 0 to 0.3, we mean try to model the ad stock for Facebook so that like the decay of the Facebook's media effect is between 0 to 30%.
Okay,
that's
so
what
like
we're trying to say.
You could decide on different channels to measure that decay differently. So like, for instance, if you have some channels you consider more upper funnel versus lower funnel, you could change the decay ratio, or if you had some channels you considered more likely to get a first click than a last click, this is where you can go in and kind of weight those channels. Is that what we're looking at essentially?
Right. Yeah.
Okay, thank you. Hold on. So why don't we spend a little bit of time on that? Mari, if you're still in class, can you, first of all, sorry, Suji, I was sending out emails. Did you cover the benchmarks that Robin gives for these channels? You did?
Right.
Right.
So on top of the, yes.
Right there. Okay.
Yep.
These are different benchmarks that they offer, and he's already copied that over and can adjusted it for different channels in that particular use case. Mari, how would you pick those? Maybe can you like spend 5 minutes on why you would pick, variable versus geometric, and how will you set up the wider or tighter based on our understanding?
Right. First of all, depends on the media type. We are going to specify the decay rate, right? So in this example, you could see that for digital, the recommended value is between 0 and 0.3, right? So when the value of 0, the value of 0 means there is no decay, right? Which means that the impressions, whatever you see at a particular time point, that's it. It's not going to carry over to the next week. So if it is 0.3, which means 30% would be carried over to the next week, and then 30% of that 30% would be carried over to the week after that. That is how we should interpret. So depending on the funnel type of the media, the values can range, right? For example, for the upper funnel media channel, we could say that the decay rate could be much, the decay could be much slower, let's say 0.8, which means that the retention rate is 0.8, right? The 80% is going to be retained or carried over to the next weeks. And then moving on to the variable CDF. In this case, in case of geometric, the rate is actually fixed, right? The decay rate is fixed. Probably you can show that plot, Suji.
Right.
Yeah. So you could see that the first plot is referring to the geometric ad stock, which has the fixed decay rate, right? Which means that let's say the retention rate is 50%, that 50% is constant across the time, right? But in case of variable CDF, that is not fixed. So at let's say at time point 2, it can have a decay rate of 50%, and then at time point 3, it can have a decay rate of maybe 40%, right? So the variable CDF is going to support a variable decay rate when compared to the geometric. Okay, does that make sense? So in the second plot, you could see that, for example, for the last one, you could see that it is not decaying for a while, right? It stays at 100%, which means that the effect is going to stay at 100% for a while, and then it starts decaying. So depending on how the media is going to function, and we can vary these values, right? But if you have to be a little careful, because this can literally go and find spurious relationships with the data. Literally, it can find correlations which may not make sense. So sometimes you'll have to go and understand what is the value that it picked as an optimal value, plot them, and then make sure that it makes sense for your media channel. And then coming to the third one, the variable PDF, which is even more flexible, right? It can support flexible decay rate, and at the same time, it can also support delayed peak effect, right? So for example, in the other two methods, you saw that the effect of the media is 100% right after the execution, right? Which means that the media is assumed to have the 100% effect after its execution. But in case of variable PDF, maybe some channels, as soon as the ad is shown, it is not going to probably have an effect. The effect would be built over the time, right? For such kind of media, we can probably go for variable PDF, which is the third one. Could see that it can act in various forms. It can act like a geometric, or it can act like a variable CDF, or it can act like a function having a delayed peak effect, right? So the third one is a more flexible form. But what we have seen is that sometimes, if you're not conscious of the range that you're giving for a given media channel, it can find some values which may not make business sense, right? So it is always recommended to plot these values once they are selected and make sure they make sense. Any questions on that?
I do have a question on that.
Yeah.
So when you're testing the model, does it look at each channel first and then say, this is the decay rate that makes sense? Or is there just an assumption placed on it and you have to train the model to then understand if what you set perhaps doesn't make sense for that channel?
So it is not sequentially found, these optimal parameters. So that's why we are giving a range. Let's say between 0.3 to 0.8. There are probably millions of values between these two range, right? So essentially, Robin is going to run the whole model. It runs an algorithm called Nevergrad optimization algorithm, which is going to move towards the range of parameters, or towards the values, which actually reduces the overall error, right? It could be the training error or the validation error, depending on what we set. So it is not sequentially found, if that answers your question.
Yeah, makes sense.
Just to add, as Mari mentioned, Robin is using like an evolutionary algorithm, never that. So it will see what is working and it tries to align to that region, when it's trying to pick these parameters. And also, when I'll be sharing that, when I'll be sharing the best practices document, you would see more of those cases. I think here is one of the cases where you mentioned, there are cases where some of these parameters wouldn't make sense. This is one example of that.
Yeah. Suji, let me probably just spend 1 minute on this.
Sure.
So this is one interesting example that, when we were working for a client, so we just blindly use the variable PDF, right? Which has various forms, which is very flexible. Then we saw that the R squared to be very high, about 90%. And almost all the channels were getting contribution. And we were happy with the results. But when we went and looked at their shapes, it was not really making sense. For example, for let's say branded search, we may expect, let's say, a click, right? We may expect the effect of that click to happen right away, not after some days, right? So, for example, here in this case, on the left, you could see that the model is suggesting that Apple search brand and the search brand has a delayed peak effect. So the effect is right after the click, the effect is 0, but after a few days, it has its maximum effect. Which means that probably this is not so plausible from the business point of view. We would expect the effect to be immediate for at least for this kind of really lower funnel channels, right? So that is why always just don't go by the R square and MAPE values. Please look at all these, your hyperparameters values as well to see if it makes sense. Yeah, Suji.
Yeah. Thank you, Madi, for coming in. And yeah, so the next part after the hyperparameters is just executing model Robin run, which just does the modeling work. And here the important parameters for you to set is like the iterations and trials. So although we are given 1,000 here, it is usually suggested to actually run at least 2,000 iterations. And when you say trials, it means like you're starting from a new random moment in time. Like you have a random number of coefficients and you start from there and you run 1,000. In this case, 1,000 iterations with those coefficients trying to tune those. So that is one trial with 1,000 iterations. And another trial would mean like you're starting from other random part and you're again running 1,000. So it's just trying to mimic like what all possibilities there can be. And the TS validation equal to true parameter will ensure like you have some data kept for training, some data kept for validation, and some data kept for testing. So that is what this does. And the important thing to note there is how Robin does it. This is something that you need to take into consideration. I'll just go by it quickly. So when you have a channel, like if you have a channel which has only campaigns that are running towards the end of the modeling window, and you say like 80% of the data only needs to be used for training, what Robin does is it takes the 80% in a sequential way. So the last few months where the campaign ran might not be used for training. It might get used only for validation and testing. So it won't use that, and you should be aware of this when trying to set up the train validation and test parameter. In such cases, you need to set it in such a way that it is captured in the training data. And once you run that, you would be seeing something like happening. You would see it is running each trial 1 of 5, 2 of 5. And this is slightly time-consuming process based on the type of machine that you spin up. And it would give a final message, like whether it was able to converge or not. So in this case, for this test run, it did not converge. I didn't run for much iterations, but what you would want to see is it has to say like both of these converge. So what these parameters mean is that Nevergrad does the optimization for two things. One is the business fit, and second is the statistical fit. The business fit means the metric for that is DCOM RSST, which basically states if you're spending 60% of your money in TV, you at least you want to see 60% of those effects to come up, like the response also to come from TV. So that is what it's trying to converge to. The spend and the response should match. And the other parameter is the statistical fit. Like, does it make sense statistically? The root mean square error, like, does that get minimized? So those are two things which Robin tries to optimize for. And what you can note here is these two parameters, which we can use later when we are combining all these results together. Once you run that, you would see you would have an extra folder coming up here, which is that model run and the results select. And there is one more function, Robin outputs, just to write all those outputs. And that is when you see this folder. So there you see it selects a Pareto front. You can mention how many Pareto fronts you want. And what that means is, let me just try to find that. Yeah. So this is the plot that it gives you at the end. And all these dots that you see are the models that it ran. It's like 10,000 dots you would see here, and how many iterations it ran for. And you would see it starting, all the dots were here, and when it progresses, it would come towards the left bottom, where it has the minimum decomp RCT error and the normalized root mean square error. And these are the models that you actually want. And the line you see here is the Pareto trend. And what that signifies is like it's a Pareto optimal trend where like you cannot optimize this model any further without losing the quality of the other parameter. Like you can try to reduce decomp but it would increase the root mean square error. So that is what it's trying to say. So these are the best models, and we just selected one trend, and that is what it signifies. And you can say like we need at least 10 candidates in a Pareto to consider that. And once you have that, and you see this folder, there are a lot of files that gets generated. There is a model one-pager file, which gives you details about a single model run. Try to zoom it out. You will see all of these outputs. I'll just come back to it in a moment. And you would see how the training went, how the train test and validation errors reduced as the iterations and trials went by. And you will also see how the seasonality trends and holiday variables were computed. Give me a moment here. Fine. The system doesn't want to go. Okay. Yeah, so you have seasonality, the dependent variable, the events that you mentioned, like maybe the holidays or Black Friday events. So they give you all this data at the end, and this is for each and every model that you see here. And what our last bit of code does, see at the end, is combine all these results. So you can mention the models that you want to select. So you're saying you want to select all the models which has a normalized root mean square error less than 0.5. Similarly for the RSST error, and you want to have all the models which have R square greater than 0.8. And even you can filter by certain ranges, like some of the clients want their data by year or quarter, so you can filter the outputs just based on that if you want to. And you run this code, and you would get a combined result Excel sheet generated for you, which you can just click and view file. It would show you an option to download it. And you can click on keep, it will download it for you. And how that looks like is this. So it selects the top models which meets your criteria, and these are all model IDs. And it gives an average of it, because not one model, like a single model is not accurate. Like the way we do it is like we take an average of these models and we say like there is some level of approximation here. You can go up and down by a standard deviation, and there's some level of confidence interval for what we are saying here. And within that range, like how these media spends are like how the medias are contributing towards that dependent variable or the response, and how much of it is media and how much of it is the base variables, and you get this complete result here in this one Excel sheet. So this is what we provide in the script. And coming back to the results page,
Hang tight for 1 second. Just go back to the output for a second, Suji. Now, this is where we bridge. This is the bridge to triangulation. If you remember in the laser away case study and all the other case studies, you might have remembered this heat map. This heat map is now the decomps for the model, and this is what goes into triangulation, and that's what then pumps into all the triangulation-based optimization you do. Okay, so this is I just want you to know that here is where you're going to land if you're a wingman doing models. This is the output that bridges to everything else, right? You're trying to get here and analyze this data and figure out how to use this. Okay, all of the stuff is to get to this particular outcome. All right, keep going, Suji.
Yeah, also one thing I missed to mention here, you can also see all the parameters, like the metrics that we are calculating, it's shown here. And we always select, like we have sorted it in a way that you have the best R-square models at the front. If you want to select one single model, but that is not regularly the case. We always select a range of it and go to triangulation, as Madan mentioned. So yeah, the other outputs that you see here is the hyperparameters space. So this adds up to what we discussed earlier. When we give a range of values, here you would see how it is getting used, how the alphas, gammas, and thetas change when it is progressing through these iterations and trials, and how it got to the final value. You see the peaks in these violin charts. Those are the values that is more confidence on. And we discussed the Pareto trend profit. And there is one more graph, which is the ROAS or the CPA distribution convergence graph. Like here, you would see these beautiful plots, which shows you how it converges on the ROAS as it progresses through these iterations. So how you want to interpret and use this plot is that you want to see a good, strong peak, a tall one, not multiple peaks like in this case. So when you see a single strong peak, and usually that is the case when you run more iterations, by the end of it, you would see like a one strong peak coming at the end. That means it is confident enough. Like this is going to be the ROAS based on all the other assumptions. When you see two peaks, it's like in two minds. Okay, this also works and the other one also works. So it's you would see widely different results in the models that you see at the end. So when you see a single peak, that usually you can be confident that yeah, it works fine. And coming back to the single model one pager. So when you take a one pager of a model, it has several components to it. The first one is the waterfall chart, which shows how each of the variables are contributing towards the response. And all of this will add up to 100 in this case. And yeah, this is, I think, straightforward. You would see like the basis intercept is 48% and the competitor sales is contributing 39. So you would want to understand like why it is like this. We see like our model didn't converge. And even at the top here, it will give you the parameters, the metrics for this single model. How it worked for train, how it worked for validation, how it worked for test, all that parameters are provided here. And on the right-hand side, you would see the fit chart, how the actual versus predicted looks like. So you can see fit, in this case, it maybe even an overfit, we can say. So it missed some of the peaks here, you would see. Even here, and those are things that you need to note when you're looking at this plot. So maybe there was some event over there that we missed to capture in the input data. And the range which you had given for the train test was 50 to 80%. And you would see like at the finally it shows like 77% of the data for training and the rest for validation and test. And the next one is the total spend versus effect. In this chart, it will show you how the spend and the effect actually matches. So this would only add up to the media variables. So we are only considering the media variables here. So you're saying if you take just the spend, TV spend was 21% out of all the media variables, and it contributed to 24% of the revenue. So that is what this graph says. And similarly for each other variable, you see for out of home, there is a massive discrepancy here. So those are things that you want to look into. And there would be one more graph when you decide to cluster the results. Yeah, I think in this case, we didn't run that. There was an option in here when you output those results, there's an option to cluster these results. And when you do that, it will combine the results from similar models into one output. So that is when you see that. And here you would see how the geometric add stock has affected, like what are the thetas affected, theta selected for each of the variables. And for each variable, what was the immediate and the carryover effect. So you see for TV, it showed like 81% immediate effect and 19% was carried over due to that stock. So that is how that graph works. And the last one is there's the response curve. And this is the result from the hill function you would see here. And these dots are the mean spent for each of these channels. And the shaded area are the carryover spend. So those are the spend that was carried over from previous weeks. And this is not the kind of result that you would usually want, like the exponential peaking. You would normally see an extra curve or like this kind of a curve that gets to a point where it has diminishing returns. And the last one is the fitted versus residual plot. And here, this helps in understanding how good is your fit. And you would want this plot to more or less be a horizontal line. This blue line, it should more or less align with the horizontal axis. And the dots, you would want it to be somewhere around the x-axis. You don't want it spread out too much, meaning like you have so many outliers, you need to add more variables to make sense of it. So that is how you would use this plot. And that is all about the model one pager search. And I think that covers the code demo. And coming back to the best practices document, there are two sets of document here. One of this is a deck, which we're trying to move over to a complete wiki, which combines all of this information. So this deck is more or less covering some topics like the step-by-step process of how you would do a media mix project. So you need to understand the business questions, what kind of data you can get, how you do the data collection, what are you trying to model towards, and how you need to organize your data, what kind of information you need to capture from each of the data files that you get from the client or your own data. That is one thing. And what are different types of variables that you have? The media variables, dependent variables, the other macroeconomic factors. The document covers all of that information. How to set up your metrics, whether you want to use continuous data or categorical data. And also the granularity of data. Always having granular data would be good in all cases. as much granularity you get, the more actionable results you get into. For example, the display channels or like the digital channels. If you can split it up into campaigns, better. And even the response data, if you can get it at geo level, better. So this document goes through all of that. You have a data review part, how to handle missing data, autoregressive term, how to add autoregressive terms, how to handle multicollinearity, and how to set up your platform attribution. Like initially, when you get it, you would have a baseline. You need to set a baseline for your triangulation analysis. So just set it up before you start modeling, so you know what to expect once you do the modeling and how far off you are. And it also explains the points that we mentioned earlier, like during modeling, which variables you want to use, and how to be careful about the modeling window. And even this one would help you understand which ad stock function would be better for the channels that you have. And we also go through the model selection process in this document. And we cover a bit about triangulation analysis. This is like the output that we saw from the Excel that we exported. Yeah, and we finally come at the multiplier stage, like how we combine all this data, put it into one sheet to calculate the multipliers, so that you have a final result from a triangulation analysis. And you can take a decision on whether you want to scale it up or reduce your spend, or you want to increase it, all those details. So everything will be covered here. There are a few additional parts also, model calibration and budget allocation. So these are steps we are adding it here because it's possible in Robin, but yeah, we don't usually do it. We rely on triangulation analysis more than this. So, but if you have a geo test result, you can definitely try running calibration with Robin. There's also option for budget allocation. So we'll go into detail with all of this document. So you have all the learning materials that you need to do all of this with the workbench.
Is the wiki ready, Suji? Not yet, right?
I think there are 2 more sections to cover in that, but it's almost ready. So I'll just, how would it look like is this. You would have a page here with different topics that you can go into, and even the FAQ document with the questions that we'll be constantly updating. We'll have a regular meetings and we'll be updating these. So yeah, we'll be sharing it out once it's